Hello, everybody. My name is Aksel Haugen. I am from SINTEF, and I am the work package leader for work package 2 on CO2 transport. The objective of this work package is to remove the technical barriers to large-scale transport of CO2. And the work in this work package has been performed by TNO, by Imperial College, by IFE, and by SINTEF. Next slide, please. Here you can see a simple illustration of a CO2 transportation chain. Transport is sometimes a little bit underestimated part of the full CCS chain, but it really has some important challenges, and we have tried to address these in the Align project. The figure shows the CO2 transport chain, including the preparation for transport, that is intermediate storage after liquefaction. It's loading onto a ship. Then you have the unloading, for instance, to either to a hub onshore or to an offshore injection place. In between, we have need for temporary storage of the CO2, and if we have a hub on shore, we need also a pipeline transporting the CO2 to the injection site offshore. So this is an illustration of one of several configurations for how CO2 transport chain may be set up. There were 4 tasks. Task 2.1 on technological challenges of CO2 shipping and offshore offloading was performed mostly by SINTEF, while task 2.2, safe and efficient injection conditions for batchwise injection of CO2 from transportation vessels, was led by TNO. IFE, as you've seen from the video, was in charge of task 2.3 on the CO2 composition and defining safe operation windows, while Imperial College was in charge of flexible transport and storage networks, the last task here. I will give you some flavors of what has been done in each of these tasks. This is, of course, to the extent that a few minutes can give full justice to all the good work that has been performed here. Next slide, please. We have focused strongly on transport by ship and at both low and medium pressure conditions. Low pressure conditions means at 7 bar, temperature down to -50 degrees Celsius, while medium pressure means around at 15 bars and minus 28, around -28 degrees C. The focus of the work was to report on liquefied CO2 transport by ship, both at low and medium pressure conditions, and unloading challenges before offshore storage, and do this by means of a benchmarking study and cost estimation of CO2 transport by ship and offshore unloading. The transportation strategy will influence pre-treatment of the CO2 before transport and conditioning, before injection, which are important cost considerations for the CO2 transport and storage network design. And the work we've done focuses on shipping cost optimization, and then there is a model developed for such optimization, which has been used to assess 3 shipping transport configurations for CO2 transport with the 2 different design pressures. This has been done for the Norwegian value chain, which has been studied in Align CCUS. And each configuration reflected the different transport options for injection in the Aurora formation, which we have talked about already. We also have looked at injection directly from ships through a buoy system, and the last one allows injection from an FPSO, which is a floating production, storage, and offloading vessel. It has been shown that the low pressure 7 bar has slightly lower cost than the medium bar pressure for all the configurations, and the medium pressure has higher transport and intermediate storage cost, which is greater than the lower conditioning costs. Injection from the ship is the least cost option, followed by offshore pipeline injection from the hub, for instance at Kolsnes, and then the FPSO. Scaling up of injection ship costs was obtained from linear extrapolation and the economies of scale, rule implementation for the relevant elements, and we recommend further detailed design studies also. We found that the chosen FPSO design was not compatible with the relatively modest CO2 supply assumed in this study, which resulted in higher costs. So smaller FPSO options could result, we think, in lower costs. Next slide, please. The CO2 that comes from a capture plant contains CO2, some impurities in low concentration, as Gaute Svenningsen pointed to in the video. Even though these concentrations are low at the ppm level, these impurities may still, under certain circumstances, accumulate and cause problems in the CO2 handling system. There is an ISO standard from 2016 that gives no clear recommendation on CO2 composition. And since the maximum concentration of a single impurity, which is not giving chemical reactions, will depend on the concentration of other impurities and the temperature, it's not possible to give universal recommendations for safe CO2 compositions. The acceptable composition will actually be project specific. We have seen that NO2 is a bottleneck. Presence of NO2 and combination of NO2 and SO2 and oxygen seem to make the CO2 stream much more vulnerable for formation of corrosive phases. And there's a need for a model to establish the safe but not over strict CO2 specifications. One takeaway from this part of the work is that it's actually the capture end of the CO2 chain that has to deliver a CO2 quality which is acceptable to the transport and storage parts of the CO2 chain. Next slide, please. Operational flexibility and ability to employ different capture, transport, and storage options in the CCUS value chain have substantial benefits for the development of commercial CCUS networks. And such flexibility may involve choices over CO2 capture rate variations, different modes of CO2 transport via pipelines, ships, or even by lorries. Different CO2 transport network design options and choices regarding geological storage sites, opportunities, for instance, for enhanced oil recovery, that may be that's also part of the network. So the objectives of this work has been to develop an investment decision framework to enable the appraisal of such options and related uncertainties and engineering flexibilities. And these are factored into investment decisions. The real options inspired decision framework developed is an extension of the standard financial appraisal methods. It introduces the ability to explicitly quantify the effect of individual sources of uncertainty in each capture, transport, and storage option considered, and accounts for the flexibility that managers need over the timing of their investment when faced with uncertain cash flows. Next slide, please. Ships will supply CO2 to the injection site in batches as opposed to pipelines. And this part of our work has focused on the challenges associated with the batchwise delivery and injection of CO2 offshore. Fast and cold injection of CO2, because the CO2 is actually quite cold when it arrives at the platform. That may be required when we go for offshore unloading, when transport CO2 by ships. It will help minimize unloading times and increase economic feasibility of such projects. And in the line, we have modeled safe and efficient injection conditions for batch-wise injection. We have identified key performance indicators which will be required to design suitable monitoring plans. We have made 2 reports which focuses on the impacts of batch-wise injections and also on a monitoring plan for injection. Overall, we have now taken the first steps to help identify potential safety and performance indicators for batch-wise injection, which will be required as projects develop offshore monitoring plans. And we think that batch-wise injection can be done safely and effectively monitored using existing technologies and techniques. Next slide, please. Tomorrow you may have the possibility to get further questions answered by the experts. Here you can see who they are. Arne Dugstad from IFE has been responsible for the work done with impurities and corrosion. Anna Kåre from Imperial College with the modeling and costing. Anna is from Imperial College, and tomorrow you'll also meet Philip Nele from TNO, who has worked with the batch-wise injection in addition to myself with regard to the shipping transport.